Hello, my name is Louis, and I'm happy to share with you our paper, Cassandra Plus, Trading of Consistency, Latency, and Fault Tolerance in Cassandra. And this is a joint work with my students at Boston College, and it's partially funded by NSF. So this paper is about database. And traditionally, we only have one machine that is where the database is installed and clients can interact with the database. But right now, because the data becomes like so large and then we need to serve so many clients, so we have the notion of distributed database. We try to replicate our data, we try to do sharding, and then the benefit there are several of them, and then the key ones are lower latency because for clients, you don't need to go to far away machines. You can also access the machines that's closer to you, so the latency is lower. And then we can also have a scalability because with more machines, we can store more data, we can serve more clients, and of course, we have the higher availability because if there are certain failures, then supposedly the system should still be able to serve you. And then there are tons of real world systems, for example, Amazon Dynamo, Cassandra, React, and then this paper focuses on an open source one called Cassandra. So in the literature, actually, like this problem is well studied, and then the focus of this paper is using this kind of a newer generation of system called Nosql. The full name is not only SQL, it's a distributed key value storage. And in the theory community, we usually view this key value storage as a register. And because we only focus on two operations, so we also call it read-write register, and sometimes we also call it a shared key value pair. So the data is very simple. You have a key K, and then you have a value V. So two operation is read a value from a key K, or you write a value V to key K. And sometimes I will also call it as a get and set. And then the environment, because we try to model the internet so that it's a asynchronous network, meaning that the delay of the message could be arbitrary. And we focus on the client and server model, is that the server, they handle the storage of the data and then they need to serve the data upon client's request. And for client, they just invoke read or write operation. And the motivation of this paper is that we have tons of distributed storage algorithms in the literature, especially in the theory community. And then sometimes we also call it a distributed shared memory emulation because we try to emulate the framework of real registers on message passing network. So that's a kind of emulation. But the problem is that there's no thorough study on the performance of this algorithm into a real system. So we said that why don't we implement those things into a real system and compare different algorithms and study the performance and study the trade-off. So some of the key properties of this algorithm is a consistency, meaning that which version of data you can get, and then is there a relative ordering of operation between like what the client observed, and then there's a fault tolerance, like what kind of failure does the system kind of tolerate, and then also the latency. Latency is like how much time does it take to complete one of the two operations. And so like we choose the Cassandra as our base system. So why is that? Because it's a very popular, even though it's pretty old, but like it fits the model very well. And it's a kind of very common NoSQL storage. And it was inspired by Amazon DynamoDB. And now it's an open source project, but still very active. And then the design goal is similar to what I mentioned before. First, I want to high availability. And then it originally supports eventual consistency because you want to support this high availability. And then you also have a scalability, meaning that if I add more machines, I should be able to serve more clients and increase the throughput. And then the key part why I say that it fits our model really well is that it is based on the design for quorum replication. And then if you are familiar with the DSM emulation or distributed storage algorithms in the literature, and this quorum replication is one of the key fundamental techniques that's used by many algorithms. And then that's why we are able to implement this algorithm inside Cassandra. And then there are some other things like Cassandra that provide a knob that you can tune the consistency. And then because it's based on a peer-to-peer design, so there's a minimal administration once you launch the Cassandra cluster. So two-sentence summary of this paper is what is Cassandra Plus? We adapting and implementing the existing DSM algorithm into Cassandra, and then we did with minimal changes to the original Cassandra code base. So we don't introduce a new way of communication. We don't introduce a new data structure. We use the Cassandra internal logics to implement those DSM algorithm. So that's why we are able to provide a unified and unified and fair framework to evaluate the performance and then the trade-off between different properties, performance of many existing DSM algorithms. So here is a quick summary of some of the algorithm that we have implemented. The first one is ABD, one of the most popular theoretical algorithms. And then we also implement the multi-writer one, which decompose the ABD algorithm and provide a different kind of consistency properties. And then we also have a causal memory. That causal memory is important because that is one of the strongest consistency model that you can achieve under the CAT framework. And then we also implement two of them, two other algorithms to tolerate Byzantine failure. And for SBQ, you can only tolerate, I say, my Byzantine failure because the faulty node can only temper the value, but it cannot play with the timestamp, where BSR is a fully Byzantine, meaning that it can modify anything. And then here is the theoretical kind of analysis of a round trip time to complete an operation. And then this two is that under a certain configuration, what would be the ratio between the base system, where Cassandra 1, meaning that it doesn't really provide any kind of consistency, it just provides eventual consistency. So that's our baseline. And then as you can see that, yes, for the kind of a more theoretical algorithm, we are incurring kind of some penalty or overhead, so the throughput drops. But if you care about a certain consistency model, actually this performance is not too bad. Example, like you have this causal consistency and you do some minor kind of, you invoke some, you incur some of the minor overhead, but you provide much more useful consistency. And then of course, some of them for the Byzantine one, because you need more communication, so the read and write ratio are not too good. However, the read, if it's really read heavy, then it's okay. Okay. So here is two of the example plot that we show in the paper. So I tell you that, okay, in terms of scalability, what happens to when you have more clients and more read and write requests. And as you can see that if you choose the proper algorithm to use, the latency, especially the read latency, isn't too bad. But of course, write latency, like because we need more communication in order to achieve this kind of stronger consistency or stronger fault tolerance. Yeah, it's not as good. But here comes a summary: is that we provide a very useful framework that to fairly compare the performance and then study the trade-off. And then in short, many of the DSM algorithm have a okay performance, but the property is a much strengthened. So that's we call our system as a Cassandra plus. Okay, that's all I want to share. Thank you.